Welcome to this lecture series in group theory. Let us recall a few things that we need to follow this lecture. So we saw that if phi is a group homomorphism, then the set of all the left cosets of the kernel of phi, which is written G mod kernel phi, is precisely the set of all the fibers of phi. So recall that a fiber of phi, which is a set theoretic concept, is defined as things of this sort, where you pick any little h in the target and consider all the elements of G which map to little h. Then any such thing is a fiber. So fibers could also be empty, but what we are saying is that the set of all the non-empty fibers, they are precisely these things. All right. So further, so we get a set theoretic diagram like this. Phi is just a map, and it factors through the set of its fibers in this fashion, where of course phi bar takes G kernel phi to phi G. So basically, this diagram commutes, meaning if you go this way or you go that way, it's the same thing. All right, but what we ask the question, can we upgrade this diagram to a diagram of groups? Meaning, can we endow this object with a group structure? These two already have group structures, but can we endow this also with a group structure such that this map and that map become a group homomorphism? And we saw that the answer to that is yes, and there is a unique group structure which does that, and that group structure satisfies this property. So the binary operation takes two elements of G mod curve phi, and their quote unquote multiplication is that, and we discussed at length as to how we arrived at it. Anyway, so these are the problems. And now let us get started with the material of this lecture. So to repeat myself, we saw that G mod kernel phi can be given a natural group structure when this is a group homomorphism. The question we are asking is, what subgroups of the group G, what subgroups H of the group G are such that this can be given a group structure in the same way. So the same way simply means a group structure on G mod H such that this map is a group homomorphism, where this map is nothing but the one which takes little g to the left coset which contains G. So that is the question that we want to ask. Which subgroups, maybe not all subgroups have that property, a priori we don't know. So which subgroups have the property that this can be given a group structure so that this becomes a group homomorphism? All right, so the rest of the lecture will be to answer this question. So first we need to discuss a lemma, and we again need a notation. So this notation we discussed the last time, so let me do that in the previous page. So let G be a group, and we have two subsets, non-empty subsets of the group G. Then we define AB as that. So given any two subsets of the group G, non-empty subsets, we can create another subset of the group G in this fashion. All right. So now the lemma that we want to discuss is the following. Fix a group G and a subgroup of it. The subgroup's name is H. Then the following two things are equivalent. So the first condition says that this set, which is, think of this as A and think of that as B. So this set equals that set for all X and Y in G. And the second condition is a weird looking condition. So what is this? This is, by definition, GH G inverse, little g and capital G. So this happens for all G. So these two conditions, of course, look very, very different, but we'll show that they are actually equivalent. So let us show that one implies two. Right, maybe I should erase that. Yeah, so fix, so we assume one and fix a little g. And we want to show that GH, G inverse is contained in H. Of course, we are assuming 1. Okay, so by 1, we have GH, G inverse H is G inverse H, which is of course equal to H. So this implies in particular that little g, little h, which is a member of that thing, and G inverse E is the identity of the group. So this is a member of that thing, and therefore this product is a member of that. This belongs to capital H, which implies G inverse belongs to capital H. So here little h was completely arbitrarily chosen in capital H, and we concluded that this is the case, which just means that G inverse is contained in H, and therefore 2 holds. Okay, so now we will do 2 implies 1. This is even more straightforward, or maybe not, let's see. So let x and y in G be arbitrary, and we are assuming 2, we want to show that. Okay, so then x h1 y h2, this is a member of, so we picked an arbitrary member of that thing. H1 and H2 we have picked arbitrarily from H. So this thing is an arbitrary member of that. And let us analyze what this is. So this is equal to, and this is a little bit of a trick here. So this is equal to x, y, y inverse, h1, y, h2. All we did was we inserted an identity here, which we have written as y inverse, so that we can get xy on one side. So this is equal to, let me put a bracket here. And now just look at this expression. By 2, this expression is actually an element of H, because just think of this as think of y as G inverse in this equation or whatever. Just think of y as G inverse, then this thing is a member of H, right? So basically this whole thing is a member of XYH, because this is a member of H and that is of course in H. So this product is also in H, and therefore this thing is in that. So we started with an arbitrary member of that thing and ended up showing that it lies here. So what we have shown so far is that this containment happens. So we need to do the reverse containment. So for the reverse containment, let H and H be arbitrary. So then what we want to show is that this guy is in this set. So that's what we want to show. But this guy is equal to XEYH, which is in XHYH. And thus this is contained in. Why? Because we started with an arbitrary element of this guy and we ended up showing that it's actually here. So therefore this is contained in that. And with these two containments, this one and that one, we see that indeed this is equal to that, and we are done. So these two conditions are actually equivalent. Okay. And now we will show another equivalence. So again, G be a group and H be a subgroup of G. Then this condition and that condition are the same. So this containment can be upgraded to an equality. This was the second condition in the previous lemma. Now it becomes the first condition. So we have a further equivalence basically. Okay, so give me a moment. Yeah, so let's see why this holds. Clearly 2 implies 1. We will just do the proof of 1 implies 2. Right, so let G in G be arbitrary and H in H be arbitrary. So we are assuming 1 and we want to show that little h, we want to really show this containment because the reverse containment is already there in 1. And to show this containment, we just want to show that little h is a member of that. Okay. So now, by 1, we have G inverse Hg is contained in H. Because this holds for all G, so I can replace this thing with any element of G, and I choose G inverse. Okay, so therefore, G inverse little hg is an element of H, which implies, if you think a little bit about it, this means little h is in GHG inverse. And that's it. So since H was completely arbitrary, we have this containment. And by 1, this is also contained in H. So this sandwich gives us that actually we have an equality. Thus, H is equal to GHG inverse and G was also completely arbitrary. So this is for all G, and we are done. Right, so this weak looking thing is actually an equality. Of course, if we were working in the finite setting, if the group H was finite, I mean the subgroup H was finite, then this containment automatically implies this equality because the size of this and the size of that are the same. Okay, so combining the previous two lemmas, we get this, that if we have a group G and a subgroup H, then these three things are equivalent. We're just combining the previous two things. Right, so let's move on. Yeah, and this gives us a definition. So G be a group, N, we'll use the symbol N. So let N be a subgroup. We say that N is a normal subgroup of G if any of the three conditions that we saw are satisfied. In particular, if this is satisfied for all G in G, let me write it for all G in capital G. It's not written very neatly. G and G inverse. Yeah. So we say that given subgroup is a normal subgroup if this equation is satisfied for all G, or equivalently any of these three things are satisfied. Okay, so we have a notion of normality, and well, we'll see that not all subgroups are normal. Maybe not in this lecture, but we will see that eventually. Let's see. So now we can answer that question that we raised at the beginning of this lecture. Suppose we have a subgroup H, and we have a binary operation on G mod H, such that first of all this is a group. And now if we assume that this map, the natural projection map, which takes little g to the corresponding left coset, is a group homomorphism, then it follows that H is a normal subgroup of the group G, and the binary operation is actually just the product that we discussed earlier. So just think of this as capital A and think of that as capital B. Then this is AB, which is A, B, A, and B and B. So that's a very nice result. So we have a characterization for what subgroups have the property that once you endow them with a group structure with the additional property that the natural projection is a group homomorphism, those are precisely the normal subgroups that we just defined, and the binary operation is also unique. It's just this kind of product that we saw earlier. Okay, so first let us prove normality. So first we will prove normality. So let little g be fixed, some arbitrary element. Then pi g square equals pi g star pi g by the fact that pi is a group homomorphism, which is equal to, by definition of pi, gh star gh, which is also equal to g little h star gh, where h little h is some arbitrary element of capital H. So maybe I should write that also. So little g is in G and little h is in H. Then, so we have this much, but this is equal to pi gh star pi g, which is equal to pi GHG, right? So what we have seen so far is, so therefore pi g square equals pi GHG, which implies, which way I should multiply? Yeah, so this implies EH equals, not EH, sorry, this is just this is actually pi EG equals, I will explain this, what happened. So, okay, so this is identity of G mod H, really. What I have done is I've just multiplied by the inverse of this on the right side of both the elements. So here I get this, and here I get the identity of G mod H, but the identity of G mod H is the image of the identity of the group G under pi, because pi takes identity to identity because pi is a group homomorphism. Okay, so we have that, but what is the right hand side? This is pi GH G pi G to the minus 2, which is by homomorphism property equal to that. But since I'm out of space, I will just write that as this in one single step. Okay, so we have pi g h g inverse is pi of identity. But what is pi of identity of g? It is equal to h by definition of pi. So we have h equals pi g h g inverse. Yeah, okay, so let me also skip that step. So pi g h g inverse is nothing but the corresponding left coset. So we have g h g inverse h. So this is what we conclude. So for any little g in capital G and any little h in capital H, we have this equation. And this implies, thus, GH, G inverse is in H. So since little h was completely arbitrary, this implies GH, G inverse is contained in H. This is true for all G because little g was also arbitrary, which we saw is equivalent to saying that H is normal. So H is normal in G. So H is a normal subgroup of G. We have proven normality. And now we want to show that actually the binary operation is also a very simple one. So now we have already established normality. So we have pi xy. So we have for x and y in G, pi xy equals pi x star pi y. By definition, by the fact that pi is a group homomorphism. Now by definition of pi, we have the left hand side is that, the right hand side is that. But now since H is a normal subgroup, we saw that this thing is equal to xh yh. So therefore, this binary operation is actually the one that we mentioned in the lemma. So that proves it. So if you have a subgroup of G with some group structure on the set of left cosets, such that this is a group homomorphism, we see that there is only one such group structure, if at all there is one, and that exists if and only if the subgroup is a normal subgroup. Okay, so that's the thing. And let me end with one notation. Yeah, I want to discuss this notation. So instead of writing this H is normal in G, we just use this notation H, or N in this case, N with this triangle and a, this horizontal or slant line below it, and G. So this is read as N is a normal subgroup of G. This means N is a subgroup of G, but if you just join that with that, it becomes a normal subgroup of G. So that's the notation. And let me conclude this lecture with this last thing, which I've said multiple times now. So if H is a subgroup such that G mod H has a group structure with the property that this is a group homomorphism, then H is normal. And the group structure here is also something that we know. And if H is normal, then the converse thing also happens. So normal subgroups have this special position, so that they, you can endow the quotient with a meaningful group structure. Okay, so I think this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.